There's something utterly mesmerizing about staring up at the night sky, those countless pinpricks of light, each one a distant sun, each one holding secrets we've barely begun to unravel. But if you really want to dive into the cosmos's deepest enigmas, you don't look at individual stars or even galaxies. You look at the places where galaxies gather in almost unimaginable numbers, where the universe's most bizarre phenomena play out on a scale so vast it defies comprehension. And few places in the known universe are as mysterious or as downright weird as the Leo cluster. Picture this, a sprawling metropolis of galaxies, thousands of them, bound together by gravity in a cosmic dance that's lasted billions of years. Galaxy clusters like this are the universe's largest structures, and the Leo cluster is one of the most peculiar. Here, the rules of physics as we know them seem to bend. Objects vanish without a trace, forces we can't explain twist space itself, and then there are the things we can't even begin to categorize: glowing anomalies, unexplained gravitational ripples, and structures that shouldn't exist according to everything we've learned about the cosmos. What makes the Leo cluster so special? Why does it feel like this corner of the universe is playing by its own rules? That's exactly what we're diving into today. We're about to explore 25 of the most baffling, mind-bending phenomena hidden within this cosmic enigma, each one a puzzle that has left astronomers scratching their heads. From ghostly radio emissions with no known source to galaxies that move in ways that defy gravity itself, this is a journey into the unknown, and by the end, you might just find yourself questioning everything you thought you knew about how the universe works. So, are you ready to step into the mystery? Let's begin. Deep in the heart of the Leo cluster, astronomers have picked up something that shouldn't be there: radio waves with no obvious origin, drifting through space like a cosmic whisper. These aren't just any radio signals. They pulse and fade in patterns that don't match anything we've ever seen before, as if the universe itself is broadcasting a code we can't decipher. The first detection sent researchers scrambling, combing through every known source: black holes, neutron stars, even distant quasars, but none of them fit. These waves seem to come from empty patches of space, voids where nothing we understand could possibly produce them. So what could be causing this? One leading theory points to dark matter, that elusive substance that makes up most of the universe's mass yet refuses to reveal itself. Some scientists speculate that certain types of dark matter particles, when they collide or decay, might release energy in the form of these strange radio waves. It's a tantalizing idea, evidence of the invisible scaffolding of the cosmos finally making itself heard. But there's a problem. No one's ever observed dark matter behaving this way before. Then there's the wilder possibility, an entirely new class of celestial object, something we haven't even imagined yet. Could there be structures or phenomena lurking in galaxy clusters that defy our current understanding of physics? The Leo cluster's radio waves don't behave like anything we've catalogued. They flicker unpredictably, sometimes vanishing for years before reappearing without warning. It's as if the cluster itself is playing hide and seek with us, offering fleeting glimpses of a mystery we're only beginning to grasp. And here's the truly unsettling part. Whatever's producing these signals, it's happening on a scale that dwarfs anything we've seen. The energy required to generate such widespread, powerful radio emissions is staggering. If it's not dark matter and it's not a known astrophysical object, then what kind of cosmic engine could be at work? The more we study these phantom waves, the clearer it becomes. We're dealing with something entirely outside the playbook of modern astronomy. Until we unlock their secret, the Leo cluster will keep sending its ghostly signals, a silent challenge to anyone daring enough to listen. Among the many cosmic riddles packed into the Leo cluster, few are as unsettling as the case of the vanishing galaxy. It was first spotted decades ago, a perfectly ordinary spiral galaxy, catalogued like any other, nestled among thousands in the cluster. Then one day it simply wasn't there anymore. No explosion, no dramatic collapse, just an entire galaxy erased from the cosmos as if someone had flipped a switch. Astronomers scrambled to explain it. Could it have been a trick of the light? Gravitational lensing, the bending of light by massive objects, can distort or even duplicate distant galaxies' appearances, creating illusions. But detailed analysis ruled that out. The galaxy's position didn't align with any known lensing effects. Another theory suggested a supermassive black hole might have devoured it. While black holes are voracious, even the largest ones can't consume an entire galaxy so swiftly, and they'd leave telltale radiation bursts in their wake. This disappearance was eerily clean, leaving no debris, no energy signature, nothing. Then there's the sobering possibility of human error. Could it have been a mislabeled observation or a glitch in the data? After exhaustive reviews, that explanation also fell short. The galaxy appeared consistently across multiple telescopes over years before its disappearance. Unless every instrument malfunctioned in exactly the same way, a statistical near impossibility, something far stranger must have happened. The most radical hypothesis: that the galaxy didn't disappear at all but moved. Some theorists propose the existence of exotic physics, like hidden dimensions or quantum tunneling effects, where massive objects might briefly slip out of observable space. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, could have local distortions powerful enough to rip a galaxy from view. These ideas hover on the fringe of accepted science, but in the Leo cluster, where anomalies pile up, even fringe theories get serious consideration. What's certain is this: the debate isn't just about one missing galaxy. It's about whether our understanding of the cosmos is fundamentally incomplete. If galaxies can vanish without a trace, what else might be possible? Until we find answers, the Leo cluster's empty space where a galaxy once stood remains one of the universe's most haunting blank spots, a silent reminder of how much we still don't know. Right at the center of the Leo cluster lies a gravitational head-scratcher, a region where the laws of physics as we know them seem to unravel. Telescopes pointed at this area show something bizarre. The gravitational pull measured there is far stronger than anything the visible matter could produce. Stars orbit faster than they should. Galaxies move as if yanked by invisible strings, even accounting for dark matter, the mysterious, unseen substance thought to make up most of the universe's mass. The numbers still don't add up. This isn't just a small discrepancy. We're talking about gravitational forces up to 10 times more intense than predicted, defying every model astronomers have. The anomaly first came to light in 2014, when a team analyzing data from the Hubble Space Telescope noticed distant background galaxies appearing distorted, their light bent far more severely than expected. Follow-up observations with the European Space Agency's XMM Newton satellite revealed another oddity. The region emitted almost no X-rays, ruling out a hidden concentration of hot gas as the culprit. Then came the real shocker. Detailed mass maps showed the gravitational epicenter didn't align with any major galaxy or dark matter clump. It was just empty space tugging on everything around it with the force of a cosmic phantom limb. So what's really going on? One camp argues our dark matter models need an overhaul. Current theories suggest dark matter should be smoothly distributed in clusters, but this anomaly implies bizarre clumping or interactions we've never accounted for. Others propose something far more radical, that we're seeing hints of modified gravity, a tweak to Einstein's general relativity that would upend a century of physics. A few even speculate about primordial black holes from the early universe lurking unseen, though no evidence supports that yet. The most compelling clue: the anomaly's effects match simulations of colliding dark matter, filaments, invisible cosmic threads where dark matter densities might spike. If confirmed, it would be the first real-world evidence of these hypothetical structures. But until we can pin down the cause, this gravitational oddity remains a glaring hole in our understanding of how mass shapes the cosmos. The Leo cluster isn't just challenging what we know, it's revealing how much we've yet to learn. Deep in the heart of the Leo cluster, two cosmic oddities stand out like mismatched puzzle pieces: the twin quasar Enigma and an unstable black hole with behavior so erratic it rewrites the rulebook on how these cosmic monsters should act. At first glance, they seem unrelated, a pair of brilliant quasars flickering in sync millions of light-years apart, and a supermassive black hole that flares and dims like a malfunctioning street lamp. But look closer and a chilling possibility emerges. These might be two sides of the same cosmic mystery. The twin quasars were first dismissed as a trick of perspective, two separate objects aligned by chance. But repeated observations revealed something impossible. Despite being separated by enough space to fit dozens of galaxies, their brightness fluctuations matched perfectly, as if controlled by the same unseen hand. Quasars, the blazing cores of galaxies powered by voracious black holes, don't naturally sync up like metronomes. Yet here they were, pulsing in unison across unimaginable distances. Then there's the unstable black hole, just a few million light-years away from the twins. Unlike typical supermassive black holes that feed steadily, this one behaves like a cosmic toddler, throwing tantrums of X-rays one moment, then going eerily quiet the next. Normally, such instability suggests a recent collision or a sudden influx of gas. But this black hole sits in a relatively empty region of space, with no obvious trigger for its mood swings. Astronomers have two leading theories tying these phenomena together. The first involves binary black hole systems, pairs of supermassive black holes orbiting each other so closely that their gravitational fields intertwine. In this scenario, the twin quasars might be the visible tips of an invisible dance, their synced flickering caused by shared gas disks or warped space-time. As for the unstable black hole, it could be a third participant in this chaotic waltz, its erratic feeding patterns caused by gravitational kicks from its unseen partners. The second, even wilder theory suggests external manipulation by dark energy. Recent simulations show that concentrated dark energy, the mysterious force accelerating the universe's expansion, could create localized space-time distortions. These dark energy knots might nudge black holes into sync or disrupt their feeding patterns, explaining both the coordinated quasars and the unstable black hole's behavior. It's a radical idea, but in the Leo cluster, where normal physics often takes a backseat, even radical ideas get a hearing. What makes this duo so fascinating isn't just their individual strangeness, it's how their anomalies seem to whisper the same question: are we seeing the limits of gravity itself? Whether it's black holes communicating across cosmic distances or dark energy meddling with space-time, these phenomena challenge the very frameworks we use to understand the universe. And until we solve their riddles, the Leo cluster will keep offering up these paired mysteries, a cosmic double feature with no encore in sight. Amid the dense sea of galaxies in the Leo cluster, there's a hole, a staggering emptiness so vast it could swallow our Milky Way 100 times over and barely notice. This isn't just an ordinary gap between galaxies. It's a cosmic void, a region of near-total nothingness stretching millions of light-years, where the usual rules of galactic neighborhood seem to have been forgotten. Most galaxy clusters are bustling metropolises packed with stars, gas, and dark matter. But this void is a ghost town, an eerie blank spot in an otherwise crowded universe. Voids themselves aren't unheard of. They're part of the universe's cosmic web, the vast filamentary structure where galaxies cluster along dense threads, leaving empty bubbles in between. But voids this large, this empty, and this close to a major cluster like Leo, that's the puzzle. According to simulations, such extreme voids should be vanishingly rare, appearing maybe once in the observable universe. Yet here one sits, defying expectations like a missing piece in an otherwise perfect puzzle. What makes this void even stranger is its edges. Normally, voids transition smoothly into denser regions like a gentle slope. But the Leo void has borders so sharp they look almost artificial. Galaxies on one side are packed shoulder to shoulder, while the other side is a desolate expanse. It's as if something carved out this space deliberately, or as if some unseen force is actively preventing galaxies from drifting in. Could dark energy be responsible? Most theories assume dark energy works uniformly, pushing the universe apart at the same rate everywhere. But if it fluctuates, if it's stronger in certain regions, it might theoretically clear out galaxies like a cosmic broom. Another wild possibility involves quantum fluctuations from the early universe, frozen into space-time and expanding into these bizarre empty zones. A few researchers even speculate about primordial defects in space-time itself, leftover wrinkles from the Big Bang that could have birthed voids like this one. The most unsettling question isn't how this void formed, though it's what it's hiding. Voids aren't completely empty, they contain trace amounts of gas and dark matter. If some unknown process swept the galaxies away, where did all that material go? Could there be invisible structures lurking in the darkness, warping space in ways we can't yet detect? The Leo cluster's void doesn't just challenge our models, it dares us to rethink what empty really means in a universe that's anything but. Somewhere in the dim vastness of the Leo cluster, a cosmic alarm clock keeps going off, but no one knows who set it. In 2016, telescopes picked up a series of incredibly bright, incredibly brief radio pulses, what astronomers call fast radio bursts. These blips of energy last just milliseconds, yet pack as much power as the sun emits in 3 days. Most FRBs are one-off events, vanishing as quickly as they appear, but this one, designated FRB Leo 7, does something extraordinary. It repeats. Not on a schedule, not with any predictable rhythm, but often enough to leave scientists utterly perplexed. What makes FRB Leo 7 so baffling isn't just its stubborn reappearance, it's where it's coming from. Most repeating FRBs have been traced to the outskirts of galaxies, often near regions of intense star formation. This one, however, originates from deep inside the Leo cluster's crowded core, where galaxies jostle like commuters in a cosmic subway. The environment here is chaos incarnate. Gravitational tides rip gas clouds apart, black holes fling stars into the void, and magnetic fields twist into impossible knots. Yet somehow, amid this turmoil, FRB Leo 7 keeps firing its enigmatic signal like a lighthouse in a hurricane. So what's causing it? The leading theory points to highly magnetized neutron stars called magnetars. When these dense stellar corpses undergo starquakes, sudden fractures in their crusts, they might release bursts of energy as radio waves. The irregular timing could stem from the chaotic environment, with gravitational forces from nearby objects triggering sporadic eruptions. But there's a hitch. Magnetar bursts usually come with X-rays or gamma rays, and FRB Leo 7 is radio only. It's as if someone took a known cosmic phenomenon and stripped away half its signature. Then there's the more speculative angle. Could this be something entirely new? Some astronomers suggest colliding neutron stars, their immense magnetic fields tangling like live wires to produce recurring sparks. Others float the idea of blitzars, hypothetical objects where a neutron star's rotation is braked so abruptly by dark matter interactions that it emits periodic shock waves. And yes, the elephant in the room, alien technosignatures, hasn't been entirely ruled out. The burst structure doesn't match any known natural pattern, though most researchers consider extraterrestrial origins a last resort explanation. The real enigma is why this FRB seems to be a cosmic outlier. Other repeating bursts appear in common neighborhoods, their behavior easier to square with existing models. FRB Leo 7, by contrast, thrives in mayhem. its very existence challenging our assumptions about how such intense energy can be generated and sustained. Every time it pulses, it's not just sending radio waves, it's sending a reminder that the universe still holds cards it hasn't shown us. Until we crack its code, this repeating burst will remain one of the Leo cluster's most tantalizing whispers, a message we can hear but not yet understand. One of the Leo cluster's most perplexing features isn't something you can see, it's something you can't. Astronomers have mapped a region where galaxies approach an invisible line in space and then stop. It's as if they've hit an unseen barrier, a cosmic no-entry sign that defies every expectation of how gravity should behave. Galaxies drifting toward this zone slow down, their trajectories bending away as if repelled by some invisible force. The effect is so pronounced that researchers initially suspected instrument error, but repeated observations confirmed it. Something in that empty patch of space is pushing back. The leading explanation points to dark matter, not as a diffuse cloud but as an enormous, coherent structure. Simulations suggest dense walls or sheets of dark matter could form during the universe's infancy, remnants of quantum fluctuations stretched to cosmic scales by the Big Bang's expansion. If such a wall cuts through the Leo cluster, its gravitational influence might act like a cushion, gently repelling galaxies that come too close. Supporting this idea, faint distortions in the cosmic microwave background, the afterglow of the Big Bang, hint at similar large-scale structures lurking throughout the universe. But there's a twist. Detailed measurements show the barrier's effects are too strong for standard dark matter models. Some researchers propose these aren't just passive walls. They might be cosmic scars, defects left over from phase transitions in the early universe. Picture boiling water. As it cools, bubbles form and collide, leaving behind tangled boundaries. If spacetime itself underwent similar shifts moments after the Big Bang, it could have frozen in flaws, domain walls, strings, or textures that now exert bizarre gravitational effects. A handful of telescopes have detected anomalous temperature variations in the cluster's gas, subtle fingerprints that might align with these exotic defects. The most radical theory that we're seeing the shadow of a higher dimension. Certain string theory models predict that our three-dimensional space could be brains floating in a higher dimensional void. Collisions or warping in these unseen dimensions might project into our universe as phantom barriers. It's a stretch, but in the Leo cluster, where normal physics falters, even the wildest ideas find traction. What makes this barrier so unsettling isn't just its existence, it's the implication that our universe might be littered with these invisible roadblocks. If dark matter walls or cosmic defects are real, they could rewrite galactic evolution models, explaining why some galaxy clusters look oddly segmented or why certain voids remain stubbornly empty. The Leo cluster's barrier isn't just a curiosity, it's a glimpse into the universe's hidden architecture, a reminder that the cosmos might be far stranger than the maps we've drawn. Light doesn't usually play tricks on us. It's the universe's most reliable messenger, traveling at a constant speed, delivering snapshots of cosmic history with unflinching precision. But in the Leo cluster, even light seems to lose its way. Astronomers have observed something deeply unsettling: galaxies whose light arrives at Earth with inexplicable delays, as if struggling through invisible cosmic molasses. Some photons arrive right on time, while others, emitted simultaneously from the same galaxy, straggle in hours, days, or even weeks later. It's not just random noise. These delays follow patterns, repeating in ways that defy conventional physics. At first, scientists dismissed the anomalies as instrumental glitches, scattered light bouncing off telescope optics or interference from Earth's atmosphere. But when the same delays appeared across multiple observatories, the hunt for a deeper explanation began. The most straightforward theory involved gravitational lensing, where massive objects warp spacetime, creating multiple paths for light to travel. Normally, this produces duplicate images of distant galaxies, but in the Leo cluster, the lensing might be so complex, caused by overlapping dark matter halos, that it stretches light's arrival times unpredictably. Yet detailed mapping revealed no known mass concentrations large enough to produce such extreme delays. Then came the radical hypotheses: could spacetime itself be behaving differently in the Leo cluster? Some quantum gravity models suggest that on microscopic scales, spacetime might be foamy, riddled with tiny, fluctuating bubbles that slow light variably as it passes through. Normally, these effects are too minuscule to notice, but if the Leo cluster sits at a cosmic intersection where these bubbles accumulate, the delays might finally become measurable. Others propose that dark energy, already known to accelerate the universe's expansion, could have localized knots where it alters the fabric of space-time, creating pockets where light drags its feet. The most unsettling possibility that the speed of light itself isn't as constant as we thought. Modern physics rests on the assumption that light speed in a vacuum is immutable. But what if extreme environments like galaxy clusters tweak this fundamental constant? A handful of theorists argue that interactions with undiscovered particles or fields could subtly slow photons without breaking other physical laws. It's a fringe idea, but in the Leo cluster, fringe ideas often become front-page news. What makes these delays so captivating isn't just their strangeness, it's the way they force us to question the very tools we use to measure the universe. If light's behavior can't be trusted, how do we calibrate cosmic distances or interpret the age of faraway galaxies? Every delayed photon from the Leo cluster carries more than just starlight. It carries a challenge to our understanding of reality itself. And until we solve this riddle, these flickering anomalies will keep reminding us that even the universe's most basic rules might still have exceptions. The Leo cluster isn't just bending the rules of physics, it's rewriting them in invisible ink. Take the case of the ghostly gamma rays, an eerie glow of high-energy radiation that suffuses the cluster with no identifiable source. These aren't the predictable gamma bursts from colliding neutron stars or the steady hum of active black holes. Instead, they flicker like a candle in a cosmic wind, appearing and vanishing in patches where no known celestial object resides. What's truly baffling is the energy signature. The rays don't match the decay patterns of any known radioactive elements or particle interactions. It's as if the cluster itself is exhaling something entirely unknown, a whisper of energy from the universe's darkest corners. One tantalizing explanation ties these gamma rays to dark matter. If dark matter particles decay or collide, some theories suggest they could produce gamma radiation as a byproduct. The Leo cluster, dense with dark matter, might be the perfect place to catch this elusive process in action. But there's a problem: the observed gamma rays are too clumpy. Dark matter should be smoothly distributed, yet these emissions are concentrated in irregular pockets, like sparks from a fire no one can see. Could dark matter be clumping in ways our models don't predict? Or is something even weirder at work, like primordial black holes, relics from the Big Bang, evaporating in fits and starts? Meanwhile, just a few degrees away from the gamma-ray puzzle, another anomaly lurks in the faint afterglow of the Big Bang itself. The cold spot, a mysterious dip in the cosmic microwave background, stretches across the sky like a shadow no one can explain. Most variations in the CMB are tiny, the result of quantum fluctuations frozen in time. But this spot is colder than it should be, as if a chunk of the early universe never quite warmed up. Some researchers argue it's a statistical fluke, a random dip in the noise. Others see it as evidence of a cosmic collision, a bruise left by our universe bumping into another in the multiverse. The cold spot's proximity to the Leo cluster raises even wilder questions. Could these phenomena be connected? If dark matter decays are producing gamma rays, might they also leave imprints on the CMB? Or could the cold spot mark a region where spacetime itself is thinner, a weak point where energy leaks into or out of other dimensions? The more we study these two oddities together, the more they seem like pieces of the same puzzle. One whispers of unseen particles, the other hints at gaps in the fabric of reality. Both defy simple explanations, pointing instead to a deeper, stranger layer of the cosmos we've only begun to scratch. What ties them together is their refusal to fit. The gamma rays ignore our catalogue of known sources. The cold spot resists conventional cosmology. In any other corner of the universe, either one would be a career-defining mystery. Here, in the Leo cluster, there are just two more entries on a growing list of cosmic anomalies. And that's the real enigma. Why does this one cluster seem to collect the universe's most stubborn secrets? Whether it's dark matter's fingerprints or a crack in spacetime, the message is clear. Something fundamental is happening here, something that might rewrite not just our understanding of galaxy clusters, but of reality itself. In the bustling heart of the Leo cluster, there's a galaxy that refuses to stay still, not in its orbit, but in its very shape. Astronomers first catalogued it as a standard spiral, its arms elegantly curled like a cosmic pinwheel. Then, just a few years later, it began to warp. The spiral structure blurred, its core bulging asymmetrically, as if an unseen hand were kneading it like dough. By the next observation window, it had morphed again, this time into a messy, elongated tangle, more like a shredded piece of paper than a grand spiral. These transformations aren't happening over millions of years, as galactic evolution typically unfolds. They're occurring within decades, a blink of an eye on cosmic timescales. At first, researchers assumed it was a rare case of galactic cannibalism, a larger galaxy tearing apart a smaller neighbor. But spectral analysis revealed no second set of stars, no telltale streams of stolen material. The galaxy seemed to be wrestling with nothing. Then came the velocity measurements. Stars in the outer regions were moving erratically, accelerating in ways that defied the gravitational pull of the visible matter. It was as if an invisible force, something with the mass of a small galaxy, were yanking on them from the shadows. Could this be a collision with a dark matter substructure? Simulations show that dense clumps of dark matter, remnants from the universe's earliest days, might lurk within galaxy clusters. If one plowed through this galaxy, its gravitational tug could distort the visible stars without leaving a trace. But there's a catch. Dark matter interactions should be smooth, not jerky. The galaxy's abrupt shape shift suggests something more violent, more chaotic, like an unseen object with complex structure. An even wilder theory involves quantum anomalies. Some speculative models propose that ultra-dense, strangelets, hypothetical chunks of strange quark matter could drift through space. If one passed through the galaxy, its immense gravity might briefly warp stellar orbits before vanishing into the void. Others point to topological defects in spacetime, knots or tears in the fabric of the universe, that could momentarily grip a galaxy like a hand squeezing a stress ball. But the most unsettling possibility, that we're seeing the galaxy react to something outside our dimension. Certain string theory models suggest higher dimensional objects might cast shadows into our universe, their gravitational influence appearing and disappearing as they move through dimensions we can't perceive. It's a stretch, but in the Leo cluster, where ordinary explanations crumble, even the most outlandish ideas get a hearing. What makes this shapeshifter so mesmerizing isn't just its fluid form. It's the implication that galaxies might not be the stable islands we've always assumed. If invisible forces can reshape them so rapidly, how many other, ordinary galaxies are secretly locked in struggles we can't see? Every time this galactic chameleon flickers into a new shape, it's not just changing itself, it's challenging our entire understanding of how galaxies live, move, and collide in the darkness. The universe, for all its vast mysteries, is surprisingly strict about bookkeeping. Every calculation, every model we have, tells us exactly how much normal matter, protons, neutrons, and electrons, the stuff that makes up stars, planets, and us, should exist. And yet, when astronomers tally up all the visible galaxies, gas clouds, and dust in the Leo cluster, they come up short, way short. Nearly half the ordinary matter predicted by our best theories is simply missing. This isn't dark matter we're talking about. This is the everyday atoms that should be visible, and their absence is one of the most stubborn puzzles in modern cosmology. Where do baryons, the technical term for this normal matter, go when they vanish? The leading suspect is the elusive warm-hot intergalactic medium, or WHIM, a web of diffuse, superheated gas laced between galaxies. This gas is so thin and so hot, millions of degrees, that it emits almost no light, making it nearly invisible to traditional telescopes. In theory, it should permeate galaxy clusters like the Leo cluster, acting as a cosmic reservoir for missing matter. But when astronomers turned X-ray telescopes toward the cluster, hoping to spot the faint glow of this ultra-hot gas, they found only traces nowhere near enough to fill the gap. That's when things got interesting. A team using the European Space Agency's Planck satellite detected something unexpected: subtle distortions in the cosmic microwave background, the afterglow of the Big Bang as it passed through the Leo cluster. These distortions hinted at a vast, diffuse cloud of ionized gas, exactly what the WHIM should look like, but stretched across distances so large, it defied detection by conventional means. The catch: even this discovery only accounted for about half the missing baryons. The rest remain unaccounted for, scattered somewhere between galaxies in a form we can't yet see. One daring hypothesis suggests these baryons might be hiding in an even more exotic state, perhaps as dark gas, a theoretical form of molecular hydrogen so cold and dense it absorbs background radiation instead of emitting it. Another idea points to primordial black holes, tiny remnants of the early universe, gobbling up baryons before they could coalesce into stars. But the most provocative theory: that the missing matter isn't missing at all, we're just looking at the universe the wrong way. If baryons are trapped in enormous, thread-like structures called cosmic filaments, stretched too thin for current telescopes to resolve, their collective mass could solve the puzzle. New instruments like the upcoming Athena X-ray Observatory aim to test this by mapping the universe's large-scale structure in unprecedented detail. What makes the Leo cluster's missing baryons so fascinating isn't just the mystery itself, it's what it reveals about our blind spots. We've built detectors to catch neutrinos, designed experiments to hunt dark matter, but ordinary atoms, they're slipping through our fingers. Every unaccounted proton in the Leo cluster is a reminder. Even the most familiar pieces of the universe still hold secrets, waiting for the right tool, the right idea to bring them into the light. Until then, this cosmic accounting error stands as one of astronomy's most humbling challenges, proof that sometimes the things we think we know best are the ones that surprise us the most. Most galaxy clusters have their share of dark matter, that invisible glue holding the cosmos together, but the Leo cluster has something far stranger, a hurricane of it. Picture a vast, silent river of dark matter, hundreds of thousands of light-years wide, barreling through the cluster at nearly 2,000 kilometers per second. It's not just drifting aimlessly. This stream is structured, moving with the precision of a cosmic freight train, dragging entire galaxies along in its wake. And here's the catch: we wouldn't even know it was there if not for the gravitational quirks it leaves behind. The first clues came from subtle distortions in starlight. As background galaxies' light passed through the Leo cluster, astronomers noticed peculiar warps that couldn't be explained by visible mass alone. Mapping these distortions revealed an elongated gravitational footprint, something massive and invisible, slicing through the cluster like a knife. Further analysis showed galaxies along this path were being tugged off course, their motions skewed as if caught in an unseen current. The culprit, a rogue stream of dark matter, possibly the shredded remains of a dwarf galaxy devoured by the cluster long ago. When smaller galaxies merge with larger ones, their dark matter halos can stretch into long, fast-moving tendrils, fading into the background unless you know where to look. But this dark matter hurricane isn't just a relic of a past collision. It's a live laboratory for testing our detection limits. Most dark matter searches focus on static halos, but this stream is dynamic, a high-speed puzzle that defies traditional methods. Particle detectors on Earth, built to catch hypothetical WIMP weakly interacting massive particles, rely on dark matter moving at predictable speeds. A stream this fast could be flying right through these experiments unnoticed, like trying to catch a bullet with a net designed for butterflies. The storm's origins deepen the mystery. Some simulations suggest it's not from a single dwarf galaxy but a group of them, a swarm of smaller systems torn apart and woven into this dark river. Others propose an even wilder source, a dark galaxy, a structure made almost entirely of dark matter, leaving no stars or gas to betray its passage. If true, it would mean such invisible galaxies might be far more common than we thought, drifting unseen through the cosmos. What makes this phenomenon so thrilling isn't just its scale, it's the way it forces us to rethink the tools we use to explore the unseen universe. If dark matter can organize itself into hurricanes, what other structures might be out there? And if something this massive can hide in plain sight, what else have we missed? The Leo cluster's dark matter storm isn't just a curiosity, it's a challenge. A cosmic wake-up call reminding us that the universe's greatest secrets might be moving right through us, silent and unstoppable. At the fringes of the Leo cluster, a cosmic nursery defies every rule in the book, a region where stars are being born in conditions so extreme, so hostile, that our current models say it shouldn't be possible. This isn't just a few outliers. Entire generations of stars are igniting in an environment that should snuff them out before they even begin. The gas here is too hot, too turbulent, and far too sparse to collapse under its own gravity. Yet somehow, against all odds, brilliant new stars light up the darkness like flares in a storm. The first red flag came when astronomers measured the temperature of the star-forming clouds. Normally, stellar nurseries are cold just a few degrees above absolute zero, because only in that frigid state can gas clump together tightly enough to trigger collapse. But in this pocket of the Leo cluster, the clouds are scorching, heated to millions of degrees by the intense radiation and shockwaves from nearby supernova. By all rights, that heat should keep the gas too agitated to form stars. Instead, observations show infant stars blazing to life right in the middle of this chaos, as if the universe has found a backdoor to bypass its own physics. One radical explanation points to modified gravity. Most star formation models rely on Newtonian gravity, but some theorists argue that in extreme environments like galaxy clusters, gravity itself might behave differently. If the force weakens less with distance than we think, or if dark matter's distribution warps spacetime in unexpected ways, it could allow gas to collapse even when conventional physics says it shouldn't. A handful of telescopes have detected peculiar gravitational lensing patterns around this region, subtle distortions that don't match standard predictions. Could this be the fingerprint of gravity playing by new rules? Then there's the wild card, external energy. Some researchers propose that colossal magnetic fields, woven through the cluster like invisible spiderwebs, might be channeling energy into these gas clouds, squeezing them just enough to tip the balance. Others wonder if dark matter particles, if they collide or decay, could deposit bursts of energy, kickstarting star formation where it otherwise wouldn't occur. The most tantalizing clue, the baby stars here are unusually rich in heavy elements, suggesting they formed from gas that's been pre-processed by some violent, unseen mechanism. What makes this stellar nursery so unsettling isn't just that it exists, it's what it implies about our cosmic blind spots. If stars can form in places our models say are impossible, How many other nurseries have we overlooked? And if the Leo cluster is hiding shortcuts to star birth, what other laws of physics might bend under the right conditions? Every newborn star in this forbidden zone is a challenge, a flickering reminder that the universe still holds mysteries no textbook could ever predict. Among the countless galaxies swirling in the Leo cluster, there's one that refuses to follow the crowd, a rebel spinning in the exact opposite direction of its neighbors. Normally, galaxies in clusters move like synchronized swimmers, their rotations aligned by the gravitational tides of the cluster itself. But this one, dubbed NGC 3267 Delta, spins backward, a cosmic contortionist defying every expectation. It's not just odd, it's statistically improbable, like finding a single clock in a room of thousands all ticking counterclockwise. The discovery sent theorists scrambling. One explanation suggests a dramatic past collision, a smaller galaxy slamming into NGC 3267 Delta at just the right angle to reverse its spin. But detailed surveys show no remnants of such a crash, no telltale debris or distorted stellar streams. Another idea involves an unusually strong interaction with dark matter. If a dense clump of dark matter passed through the galaxy's core, its gravitational tug might have flipped the rotation like a switch. Yet simulations of this scenario produce backward spins that decay within a few 100 million years, far shorter than the time this galaxy's defiance has apparently lasted. Then there's the redshift paradox, a separate but equally baffling phenomenon. Redshift, the stretching of light toward longer, redder wavelengths as objects move away from us, is the bedrock of modern cosmology. It's how we measure cosmic distances and map the universe's expansion. But in the Leo cluster, certain objects exhibit redshifts that don't match their expected motions. Some galaxies appear to be both approaching and receding simultaneously, their light signatures scrambled as if space itself can't decide which direction they're moving. Others show redshifts inconsistent with their positions in the cluster, like cars on a highway, some speeding forward while others inexplicably drift backward. One possible culprit is the cluster's immense gravitational field. Einstein's theory predicts that strong gravity can stretch light's wavelength, mimicking the effect of motion, a phenomenon called gravitational redshift. But the Leo cluster's gravitational pull, while substantial, shouldn't produce distortions this extreme unless hidden mass is warping spacetime in ways we can't detect. Another theory points to the kinetic Sunyaev-Zeldovich effect, where hot electrons in the cluster scatter cosmic microwave background photons, altering their observed energy. Yet even this can't fully account for the redshift anomalies observed here, the most provocative explanation that these discrepancies hint at physics beyond our current models. Some modified gravity theories propose that the constants governing cosmic expansion might vary in extreme environments, subtly tweaking how light redshifts over vast distances. Others speculate about dark flows, a mysterious, large-scale currents in the universe that could drag galaxies in unexpected directions, leaving redshift fingerprints that defy conventional interpretation. What ties these two enigmas together is their defiance of cosmic choreography. The backward-spinning galaxy ignores the cluster's gravitational rhythm. The redshift anomalies resist the universe's expansion script. Both suggest that in the Leo cluster, the rulebook might have missing pages, or that we're only just beginning to read them. Whether it's unseen matter, hidden dimensions, or entirely new laws of motion, one thing is clear: this cluster isn't just hosting galaxies. It's hosting mysteries that could rewrite our understanding of how the cosmos moves, and what moves it. Deep within the Leo cluster, astronomers have stumbled upon a cosmic snarl so dense it warps the very fabric of space around it. This isn't just another clump of galaxies, it's a gravitational maelstrom where the threads of the cosmic web, the vast filamentary structure connecting the universe, twist into a knot tighter than anything we've seen before. The galaxies here orbit faster, the dark matter clumps more densely, and the gravitational lensing effects are so pronounced they bend light into impossible arcs. It's as if the universe tied itself into a bow and no one can figure out why. What makes this knot so baffling isn't just its density, it's the way it defies time. Simulations of the cosmic web suggest such tight, stable knots should take billions of years to form, yet this one appears far younger than its surroundings. Some researchers argue it's a primordial fossil, a rare relic from the universe's infancy when quantum fluctuations in the newborn cosmos left behind overdensities that resisted smoothing out. If true, it's a time capsule from the first moments after the Big Bang, a place where the universe's earliest wrinkles never got ironed out. But there's a competing theory, one that sounds ripped from science fiction. This knot might be evidence of a universe in a universe. Certain brainworld models propose that our three-dimensional space could be nested within a higher dimensional reality, like a sheet of paper floating in a vast room. If another brain universe brushed against ours long ago, the collision could have left behind gravitational scars, regions where space-time is permanently knotted, trapping extra dimensions like threads in a tangle. The knot's bizarre gravitational signatures, including anomalous gravity waves detected nearby, fit eerily well with this idea, the most tantalizing clue. The knot's thermal fingerprint, gas within it is colder than expected, as if shielded from the surrounding cluster's heat by some invisible barrier. Dark matter alone can't explain this. Even its mysterious influence shouldn't create such sharp thermal boundaries. Yet if this were a brain collision site, the interface between dimensions might act like insulation, preserving pockets of older, cooler spacetime. Of course, not everyone's convinced. Skeptics point to more mundane explanations, like a recent, head-on merger between two massive dark matter halos, a cosmic traffic jam frozen in the act. Others suggest the knot is simply the densest part of a larger filament we're seeing edge on, magnifying its apparent strangeness. But with every new observation, the anomaly grows harder to dismiss. The latest radio surveys reveal magnetic fields twisted into helical patterns within the knot, a configuration never seen elsewhere in nature. Even more puzzling, these fields align neatly with the axis of a nearby void, as if the knot and the emptiness are somehow in dialogue. Whether it's a relic of creation or a door to another reality, one thing's certain: this knot isn't playing by the rules. It challenges our timelines, our models, even our understanding of dimensionality. And as telescopes peer deeper, the Leo cluster's tightest tangle keeps whispering the same unnerving question: what if the universe isn't just expanding but folded? Quasars are supposed to be the universe's lighthouses, steady, brilliant beacons powered by supermassive black holes feasting on gas at the centers of galaxies. Their light can take billions of years to reach us, and for most, that glow changes so slowly, it's practically eternal. But in the Leo cluster, one quasar refuses to follow the script. Designated LQ09, it flickers like a candle in the wind, its brightness spiking and plummeting over mere days. That's not just unusual, it's theoretically impossible. Black holes this massive shouldn't be able to vary their output so quickly. Their accretion disks, the swirling rings of superheated material that feed them, are light weeks or even light months across. Changes that fast would require the entire disk to brighten or dim in unison, like a stadium wave moving faster than the speed of light. The first clue to this quasar's erratic behavior came from automated sky surveys. Most telescopes ignore objects that vary too rapidly. They're assumed to be instrumental glitches or nearby asteroids. But LQ09 kept reappearing in the data, its wild fluctuations defying every filter. Follow-up observations confirmed it. This was a genuine quasar, billions of light years away, pulsing as if something were flicking a cosmic dimmer switch. One explanation points to microlensing, a phenomenon where an invisible object, like a rogue planet or a lone star, passes between us and the quasar, magnifying its light temporarily. The problem: micro-lensing events usually last weeks or months, not days, and they don't explain the quasar's irregular rhythm. LQ09's flickers come in no discernible pattern, sometimes flaring multiple times in a week, then going silent for months. Then there's the accretion disk instability theory. Some models suggest that under extreme conditions, these disks can develop turbulence or whirlpools that cause localized brightening. But simulations show these instabilities should smooth out over time, not produce the sharp, erratic spikes observed here, unless, of course, the disk isn't a disk at all but a swarm of smaller objects. A few theorists speculate about dark asteroids, chunks of condensed dark matter, or primordial black holes orbiting the central black hole, their collisions sparking temporary flares. It's a stretch, but in the Leo cluster, even the wildest ideas get traction, which brings us to the most controversial hypothesis: could this be artificial? The idea of a Dyson sphere, a hypothetical megastructure built by an advanced civilization to harness a star's energy, has long been science fiction. But what if something similar encircles this quasar? Irregular shadows passing across its surface might explain the abrupt dips in brightness. The biggest hurdle: scale. Constructing anything large enough to eclipse a quasar's accretion disk would require engineering beyond anything we can fathom. Yet the timing fits. The flicker's durations match what you'd expect if giant, segmented panels were rotating in front of the light source. Of course, the scientific community remains deeply skeptical of extraterrestrial explanations. But here's the twist: LQ09 isn't alone. A handful of other ultra-fast varying quasars have turned up in recent years, all with similarly baffling patterns. Whether it's lensing, instability, or something beyond our current physics, these flickering giants are forcing astronomers to confront an uncomfortable truth. Even the most well-understood objects in the universe can still surprise us. And in the Leo cluster, where surprises pile up faster than answers, this quasar's erratic glow might just be the most tantalizing clue yet that we're missing something fundamental about how black holes, or perhaps something else entirely, operate. While most planets orbit stars in predictable paths, the Leo cluster hosts a fleet of cosmic fugitives, rogue planets hurtling through space at speeds that defy explanation. These aren't your typical drifting worlds, nudged gently into the void by gravitational encounters. These are unbound planets rocketing through the cluster at hundreds of kilometers per second, velocities so extreme they shouldn't exist in this environment. Some move fast enough to escape the cluster entirely, streaking into intergalactic space like bullets fired from a cosmic gun. Where did these planetary outlaws come from? The leading theory points to violent ejections. In dense galaxy clusters, close encounters between stars can fling planets loose, like a slingshot firing a stone. But the speeds we're seeing in the Leo cluster are far beyond what standard gravitational interactions should produce. Simulations suggest something more catastrophic, perhaps a close brush with a mid-sized black hole, whose gravity could accelerate a planet to blistering speeds without capturing it. Others propose a chain reaction of near collisions, where a planet gets passed like a pinball between multiple massive stars, each kick boosting its velocity further. Then there's the capture hypothesis. Some of these rogue worlds might not be natives of the Leo cluster at all. Their trajectories and compositions hint they could be interlopers, snatched from passing galaxies during ancient collisions. Imagine a galaxy drifting too close to the cluster's core, its outer planets torn free by tidal forces and sent careening into the void. A handful even show atmospheric signatures unlike anything else in the cluster, chemical fingerprints that suggest origins in a radically different cosmic neighborhood. The real enigma is how some of these planets survive their journeys intact. At these speeds, even sparse interstellar gas should erode their atmospheres over time, yet many appear surprisingly pristine. One explanation involves magnetic fields. These worlds might generate protective bubbles, shielding themselves as they plow through the cluster. Another possibility is even stranger. Perhaps they're replenishing their atmospheres by scooping up gas from the cluster's diffuse medium, like a ship with an invisible sail. What makes these unbound planets so compelling isn't just their speed, it's what they reveal about the chaos lurking in galaxy clusters. If planets can be hurled across the cosmos like this, how many others are out there, drifting unseen between the stars? And if some truly are extragalactic refugees, they could carry secrets from distant corners of the universe, frozen in their icy surfaces or hidden in their windswept skies. The Leo cluster's rogue planets aren't just cosmic oddities, they're proof that even in the vastness of space, nothing stays in its place forever. There's a stretch of space in the Leo cluster where compasses would spin wildly, not because of some planetary magnetic field, but because the fabric of the cosmos itself seems magnetically warped. Astronomers first detected it through polarized light measurements. Across a region spanning millions of light years, the magnetic fields don't twist and tangle like they should. Instead, they line up with eerie precision, as if drawn by an invisible hand. These fields aren't just strong, they're organized, aligned along axes that don't match any known large-scale structure. It's like stumbling upon a cosmic freeway where all the cars are driving in perfect formation, with no traffic signs in sight. What could create such order in the chaos of a galaxy cluster? One possibility lies in cosmic strings, hypothetical flaws in space-time left over from the universe's birth. These ultra-dense, thread-like defects, thinner than an atom but stretching across the cosmos, might carry immense magnetic fields along their length. If one passed through the Leo cluster eons ago, it could have imprinted its magnetic signature onto the gas and dust, leaving behind this ghostly alignment. Simulations show such strings could warp spacetime subtly enough to escape direct detection while still influencing everything around them. But there's a rival theory: primordial magnetism. In the universe's first moments, before stars or galaxies formed, quantum fluctuations might have generated magnetic fields on cosmic scales. Most of these fields would have diluted away as the universe expanded unless they got trapped in regions of dense matter like galaxy clusters. The Leo cluster's aligned fields could be a fossil of that ancient magnetism, a relic from a time when the universe was a seething soup of particles and energy. Supporting this idea, the fields align with faint, filamentary structures in the cluster's outskirts, threads of gas that might trace the paths of primordial magnetic waves frozen in time. Then there's the dark matter connection. Some models suggest dark matter particles could interact weakly with magnetic fields, their collective motion amplifying and organizing ambient magnetism over billions of years. If dark matter in the Leo cluster flows along invisible channels like rivers carved into space-time, it might have sculpted these fields into their current, unnerving uniformity. Radio telescopes have spotted faint synchrotron emissions along the field lines, hinting at high-energy particles spiraling in their grip. But what's accelerating those particles? The usual suspects, supernova shocks or active black holes, don't match the emission patterns here. The most tantalizing clue might come from neighboring galaxy clusters. A few show similar magnetic alignments, all oddly parallel to the Leo cluster's fields, as if part of some vast, unseeable grid. If these regions are connected, we might be glimpsing the skeleton of the cosmic web itself, the magnetic scaffolding upon which galaxies are built. Or perhaps something even stranger, a shadow of higher dimensional physics, where our three-dimensional fields are just echoes of forces acting in realms we can't perceive. Every time astronomers map these fields, the mystery deepens. They shouldn't be so coherent over such scales, they shouldn't point where they do, and they certainly shouldn't linger unchanging in an environment as violent as a galaxy cluster. Yet here they are, a silent reminder that magnetism, one of the universe's most familiar forces, still holds secrets we've only begun to trace. Whether they're scars from the Big Bang, signatures of dark matter, or something beyond our current physics, one thing's clear: in the Leo cluster, even the invisible has a story to tell. Somewhere in the quiet void between galaxies in the Leo cluster, an echo whispers one that shouldn't exist. It arrives as a faint but unmistakable electromagnetic pulse, repeating every 17 hours like clockwork. No star, no black hole, no known celestial object sits at the source. The signal simply bounces into our telescopes as if reflecting off an invisible wall in deep space. At first, astronomers dismissed it as interference, a glitch from a passing satellite or an echo of human-made radio noise. But when the pattern persisted for years, unchanged and unyielding, the real mystery began. This echo defies conventional explanations. Its structure is too clean, too precise to be natural static, yet it carries none of the hallmarks of artificial transmission. The signal's frequency drifts slightly over time, mimicking the Doppler shift of an object moving at relativistic speeds. But calculations show nothing massive enough to produce such an effect lies along its trajectory. It's as if the pulse is emerging from empty space itself, a phantom broadcast with no transmitter. One spine-tingling possibility involves reflections from parallel universes. In certain multiverse theories, our cosmos might float alongside others in a higher dimensional bulk. If space-time is warped just right, say, by the Leo cluster's immense gravity, signals from a neighboring universe could theoretically leak into ours, bent and distorted like sound bouncing through a canyon. The echo's 17-hour cycle might then be a cosmic delay, the time it takes for the pulse to traverse the hidden geometry between realities. Supporters of this idea point to subtle anomalies in the signal's polarization, twists that resemble predictions of how higher dimensional physics might imprint on electromagnetic waves. Then there's the space-time loop hypothesis. General relativity allows for extreme gravitational fields to twist light into closed paths, trapping photons in eternal orbits around black holes or other dense objects. Could the Leo cluster's combined mass have warped space-time into a natural echo chamber, where ancient bursts of energy endlessly circle the cosmos, occasionally leaking toward Earth? If so, the original source might have vanished eons ago, a star that died billions of years back, its final scream still reverberating through the cosmic labyrinth. Of course, skeptics argue for less exotic answers. The signal might be an instrumental ghost, a rare artifact where radio waves bounce between telescopic components in unexpected ways, creating false echoes. Yet no earthly observatory has ever produced a ghost signal this persistent or mathematically pristine. Others suggest reflections of hitherto unseen structures, perhaps vast, cold clouds of plasma or dark matter with unexpected reflective properties. But none of these fully explain the echo's rhythmic precision or its peculiar spectral fingerprints. What makes this phenomenon so haunting isn't just its mystery, it's the way it plays with scale. That 17-hour interval, it matches no known cosmic rhythm, no orbital period or pulsar rotation in the observable universe. It feels almost arbitrary, as if the cosmos picked a random stopwatch and started counting. And that's the real puzzle. Echoes imply boundaries, surfaces for waves to rebound off. But in the emptiness between galaxies, what could possibly serve as that mirror? Whether it's a crack between realities, a flaw in space-time, or something beyond our current physics, this signal refuses to be ignored. Every time it pulses, it's not just repeating, it's asking a question we're not yet equipped to answer. Galaxy clusters are supposed to follow a cosmic hierarchy, a handful of massive galaxies surrounded by a sprinkling of smaller satellite galaxies, like a king with his courtiers. But the Leo cluster laughs in the face of this expectation. Here, dwarf galaxies, those tiny, faint collections of stars, outnumber their larger counterparts by an astonishing margin. There are hundreds of them, swarming the cluster like bees around a hive, far more than any simulation predicted. It's not just a slight discrepancy, it's a full-blown cosmic rebellion against our understanding of how galaxies form and gather. So why does this matter? Dwarf galaxies are more than just celestial afterthoughts, they're critical pieces of the dark matter puzzle. According to the leading cosmological model, dark matter should clump together in predictable ways, creating halos where galaxies can form. Simulations based on this model produce a specific ratio of large galaxies to small ones, and the Leo cluster's numbers throw that ratio into chaos. Either dark matter behaves differently here than we thought, or something extraordinary happened during this cluster's infancy that flooded it with dwarfs. One possibility is that the Leo cluster is a galactic graveyard, a place where countless small galaxies were torn apart by gravitational tides, their stars stripped away and scattered, leaving behind dense, dark matter-rich cores that now masquerade as dwarf galaxies. Observations support this. Many of these dwarfs are unusually compact, with far fewer stars than expected for their size. They look like the skeletal remains of larger galaxies, their outer layers shredded by the cluster's violent environment. If true, it means we might be miscounting dwarfs altogether, mistaking galactic corpses for pristine survivors. Another theory points to the cluster's unique formation history. Most galaxy clusters grow by absorbing smaller groups over time, but the Leo cluster might have gorged itself on an unusually rich diet of dwarf-rich filaments early in its life. Imagine a cosmic buffet where the Leo cluster arrived first, scooping up hundreds of dwarfs before other clusters could take their share. This would explain the surplus, but only if the universe seeded dwarf galaxies more prolifically in this region than elsewhere, a fluke that current models struggle to explain. Then there's the dark matter wild card. Some theorists argue that the surplus undermines our standard dark matter framework entirely. If dark matter particles interact with each other, not just through gravity but some unknown force, they might form smaller, more numerous halos than simulations predict. A handful of telescopes have detected peculiar gamma-ray emissions from the cluster's outskirts, faint glows that could hint at such interactions. If dark matter is more dynamic than we assumed, it could rewrite the rules of galactic formation, turning the Leo cluster's dwarf surplus from a problem into a clue. What makes this phenomenon so fascinating isn't just the numbers, it's the way it forces us to confront the gaps in our cosmic senses. Are we underestimating dwarfs because they're too faint to see? Overestimating them because we're counting ghosts of larger galaxies? Or is the Leo cluster simply a statistical outlier, a cosmic jackpot where the dice rolled in favor of the little guys? Every flickering dwarf in this crowded cluster is a question mark, a tiny challenge to the grand narrative of how galaxies and the dark matter that binds them shape the universe. And until we solve it, the Leo cluster will keep defying expectations, one dwarf at a time. Gravity is supposed to bend light in predictable ways, like a well-worn path through a cosmic forest. But in the Leo cluster, light doesn't just bend, it twists into shapes that defy every equation astronomers have. This isn't ordinary gravitational lensing, where massive objects warp spacetime to magnify distant galaxies. This is something stranger, as if the cluster contains invisible fingers tugging at light in ways no visible mass could explain. The distortions are too sharp, too asymmetrical, and they shift over time in patterns that shouldn't be possible. It's like watching a funhouse mirror rearrange itself when no one's touching the glass. The first clues came from Hubble's deep field images. Background galaxies behind the Leo cluster appeared stretched into arcs and rings, normal for lensing, but their exact positions and shapes didn't match the cluster's mapped mass. Detailed models accounting for every visible galaxy, every wisp of gas, even the inferred dark matter halo, still left glaring discrepancies. Some arcs were too tight, too bright, or split into multiple copies where there should have been none. The most striking example, a perfectly mirrored triplet of the same distant quasar, its light bent into a triangle of images with brightness variations that flickered out of sync. According to relativity, those copies should have brightened in sequence as light traveled slightly different paths. Instead, they flared randomly, as if space-time itself were shuddering. So what's warping light so unpredictably? One camp argues for rogue dark matter clumps, dense, moon-sized nuggets drifting through the cluster like invisible icebergs. These subhalos could be remnants of the universe's first seconds, pockets of pure dark matter untouched by the chaos of galaxy formation. Their gravity would sculpt light without emitting any detectable signal, leaving only these lensing oddities as clues. Supporting this, some distorted arcs trace faint, crisscrossing paths like shadows cast by unseen structures. Yet even if such clumps exist, they shouldn't be abundant enough to explain the sheer number of anomalies here. Then there's the radical alternative. Maybe gravity itself works differently in the Leo cluster. Modified Newtonian dynamics, or MOND, proposes tweaks to Einstein's equations to eliminate the need for dark matter. In most galaxies, MOND struggles to match observations, but in the extreme density of the Leo cluster, its predictions align eerily well with some lensing quirks. Certain distortions resemble simulations where gravity strengthens faster over short distances, as if the cluster's core obeys a hidden rulebook. Skeptics counter that MOND can't explain other cosmic phenomena, like the bullet cluster's separated mass and gas. But in the Leo cluster, where anomalies pile up, even fringe theories get a second look. The most tantalizing and unsettling data comes from time delays. When light takes multiple paths around a lens, some photons arrive later than others. Normally, these delays follow precise calculations. Here, they're erratic. One study clocked photons from the same burst arriving weeks apart, as if they'd slogged through unseen cosmic tar. Some theorists point to dark fluid, a hypothetical blend of dark matter and dark energy that might behave like a viscous medium in high-density regions. Others wonder if quantum foam spacetime's theorized graininess at microscopic scales could become tangible enough in the cluster's heart to slow light variably. What makes these bent light puzzles so compelling isn't just their defiance of physics, it's the way they force us to rethink the tools we use to map the unseen. Every anomalous arc, every unsynchronized flicker is a challenge. Are we missing invisible matter, misreading gravity, or glimpsing something entirely new? The Leo cluster doesn't just distort light. It distorts our certainty, reminding us that even the universe's most reliable signatures can't always be trusted. And until we solve this riddle, its twisted reflections will keep haunting our models, turning every observation into a question. The universe has a way of announcing its most violent events. Supernovas usually scream their existence across the cosmos with blinding light, swirling neutrinos, and ripples in spacetime itself. But in the Leo cluster, astronomers witnessed something that broke all the rules, a supernova that detonated in silence. No neutrino burst, no gravitational waves. Just a sudden, inexplicable flare of light where the textbook said there should have been a symphony of signals. It's like watching a bomb explode without the sound or shockwave, a cosmic magic trick that leaves physicists staring at their instruments, wondering if they've missed something fundamental about how stars die. This wasn't just a dim or distant supernova. Telescopes caught it in vivid detail, a massive star collapsing, its outer layers erupting in a brilliant flash, but none of the usual supporting evidence. Neutrino detectors, which can pick up these ghostly particles from supernovas halfway across the universe, registered nothing. Gravitational wave observatories, tuned to spacetime's faintest tremors, stayed eerily quiet. The light curve, the way the explosion brightened and faded, matched a typical core collapse supernova, but everything else about it was wrong. One explanation points to a failed supernova, a star so massive its collapse bypasses the explosion entirely, forming a black hole without the usual fireworks. In this scenario, the outer layers might have been ejected by a last gasp pulse of energy before the core vanished into darkness. But if that's the case, why did the light signature look so textbook perfect? Failed supernovas should leave behind peculiar remnants, faint, short-lived glows, not the crisp, familiar pattern astronomers observed. Then there's the quark nova hypothesis, a wild but tantalizing idea. When a neutron star forms in a supernova, unimaginable pressures might crush its neutrons into a soup of free-floating quarks, triggering a second, even more violent explosion. This quark nova could explain the silence. The initial collapse might have been too abrupt to produce neutrinos or gravitational waves in detectable amounts, while the quark-powered secondary blast emitted the light we saw. A handful of theorists argue this could also account for strange, ultra-dense cosmic objects we've spotted elsewhere, exotic stellar corpses made entirely of quark matter. But the most radical possibility, that we're seeing an entirely new kind of stellar death. Some stars might collapse in ways that shunt their energy into dimensions we can't perceive, leaving only a flicker of light as a farewell. Others could be ensnared in dark matter halos so dense they alter the physics of collapse, muffling the usual signals. Or perhaps magnetic fields, twisted to impossible strengths in the Leo cluster's turbulent environment, channeled the star's dying energy into invisible beams like a spotlight turned away from Earth. What makes this silent supernova so unsettling isn't just the missing signals. It's the way it exposes the gaps in our stellar playbook. For decades, supernovas have been reliable standard candles, their behavior predictable enough to measure cosmic distances. But if stars can die this quietly, this anomalously, how many others have we missed, and what else might they be hiding? The Leo cluster's silent supernova isn't just a puzzle, it's a warning that even the universe's loudest explosions might have secrets they're not eager to share. The silent supernova in the Leo cluster isn't just an oddity, it's a crack in the foundation of how we understand stellar deaths. For decades, astronomers have relied on a well-worn script for these cosmic explosions. A star collapses, neutrinos flood out, gravitational waves ripple through space-time, and light erupts in a predictable pattern. But this event tossed that script aside, forcing us to confront an unsettling truth. Some stars might die in ways we've never imagined. If even supernovas, the universe's most spectacular fireworks, can defy our models, what else have we gotten wrong? Consider the ripple effects on cosmic measurement. Supernovas, especially Type Ia, are standard candles, reliable beacons used to gauge distances across the universe. Their predictable brightness lets us map the cosmos's expansion, even leading to the Nobel-winning discovery of dark energy. But what if some supernovas aren't playing by the rules? The Leo cluster's silent explosion suggests entire populations of stellar deaths might be hiding in plain sight, their light visible but their other signals absent. That could skew our distance calculations, potentially altering our grasp of the universe's size and growth rate. Imagine using a ruler that occasionally shrinks without warning. That's the challenge astronomers now face. Then there's the dark matter connection. Could certain stars be so enshrouded in dense dark matter halos that their collapses are muffled? Some theories propose that dark matter particles, if they interact strongly with stellar cores, might sap energy from the explosion, diverting it into invisible channels. If true, the Leo cluster's silent supernova might be a Rosetta Stone for decoding dark matter's influence on stellar physics. Future telescopes could scan other clusters for similar events, hunting for correlations between missing signals and dark matter density. But the most profound implication isn't just about missing neutrinos or gravitational waves, it's about variety. Nature rarely settles for one size fits all, and stellar deaths might be no exception. Perhaps silent supernovas represent an entirely new class of explosion, one where magnetic fields dominate, or where exotic phases of matter like quark-gluon plasma rewrite the collapse process. The Leo cluster, with its history of cosmic rule breaking, might be the perfect laboratory to find out. What's next? Astronomers are already retuning their instruments, developing algorithms to spot quiet supernovas by their light alone, without relying on auxiliary signals. Others are revisiting old data, wondering if past events were misclassified or overlooked. And in the Leo cluster, telescopes now watch more closely, waiting for another star to die in silence and whisper secrets we're finally learning to hear. The silent supernova in the Leo cluster didn't just baffle astronomers, it ignited a race to rewrite the rules of stellar death. Teams worldwide are now scrambling to design instruments sensitive enough to catch these cosmic anomalies in the act, while theorists are tearing apart decades-old models to figure out how a star can explode without making a sound. At the forefront is the proposed EMU mission Extreme Multi-Messenger Universe, a space-based observatory that would combine neutrino detectors, gravitational wave sensors, and ultra-precise optics into a single platform. Unlike current tools that specialize in one signal type, EMU could catch even the faintest whispers of a supernova's collapse, potentially spotting neutrinos or gravitational waves too subtle for Earth-based detectors. But the real innovation lies in its AI-driven alert system, which would scan the skies in real time for discrepancies, like a supernova's light flaring without the expected supporting signals. Meanwhile, underground laboratories are pushing the boundaries of neutrino detection. The Dune experiment, buried a mile beneath South Dakota, uses liquid argon tanks to catch these elusive particles with unprecedented precision. By studying neutrinos from nearby supernovas, researchers hope to identify subtle patterns that might explain why the Leo cluster's silent supernova left no trace. One tantalizing lead comes from simulations suggesting certain massive stars might collapse so rapidly that their neutrinos become trapped in the resulting black hole's event horizon, never reaching our detectors. If true, it would mean we've been missing an entire class of implosions where the star's death cry gets swallowed by its own gravity. Theoretical breakthroughs are unfolding just as rapidly. A team at CERN recently proposed that hypothetical, sterile neutrinos, particles interacting only via gravity, might carry away energy from certain supernovas, leaving conventional detectors empty-handed. Elsewhere, string theorists are exploring brainworld scenarios where supernova energy leaks into higher dimensions, leaving our 3D universe with just a flicker of light. The wildest ideas come from quantum gravity researchers who suggest space-time foam, the seething quantum turbulence at microscopic scales, might become macroscopic in extreme environments like the Leo cluster, damping gravitational waves into undetectability. But the most promising clues might come from the cluster itself. New radio telescopes like the Square Kilometre Array are mapping its magnetic fields in stunning detail, revealing structures so intense they could bend supernova shocks into silence. Meanwhile, the James Webb Space Telescope's infrared eyes are scouring the silent supernova's aftermath for chemical fingerprints, unusual ratios of heavy elements that might hint at a quark-gluon plasma or other exotic states of matter shaping the explosion. Every observation feeds back into the models, slowly untangling whether this event was a fluke or the first glimpse of a hidden stellar death mechanism. What makes this search so electrifying isn't just the mystery, it's the stakes. If silent supernovas are common, we might be underestimating the universe's star death rate by as much as 20%, skewing our cosmic timelines. And if they're linked to dark matter or extra dimensions, their study could unlock physics beyond the standard model. The Leo cluster's silent supernova isn't just a puzzle, it's a doorway. And as telescopes peer deeper and theories grow bolder, we're not just chasing answers anymore. We're rewriting what it means for a star to die. From ghostly radio waves with no source to galaxies that vanish without a trace, from rogue planets hurled at impossible speeds to silent supernovas that defy every model, the Leo cluster isn't just a collection of cosmic oddities. It's a living laboratory where the universe tests the limits of our understanding, whispering secrets we're only beginning to decode. Think about it. Gravitational anomalies stronger than any visible mass could produce dark matter hurricanes racing through the void. quasars flickering in perfect sync across millions of light years, and entire galaxies shape-shifting before our eyes. Each of these 25 phenomena doesn't just challenge a single law of physics, it peels back a layer of the cosmos, revealing how much we still don't know. Take the cluster's missing baryons, for example. Half the ordinary matter in the universe should be there, yet it's vanished without a trace. Or the cosmic knot where gravity twists spacetime into a puzzle no simulation can untangle. Then there's the forbidden stellar nursery, where stars ignite in conditions that should snuff them out before they're born. Even light itself behaves strangely here, arriving late without explanation, as if space has unseen speed bumps. And who could forget the eerie synchronized quasars, or the supermassive black hole that flares and dims like a malfunctioning bulb? Every anomaly is a breadcrumb leading us deeper into the unknown, not just about galaxy clusters, but about dark matter, gravity, even the very fabric of reality. What ties all these mysteries together? A single, humbling truth: the universe is far stranger than our textbooks dared to imagine. The Leo cluster isn't an outlier, it's a mirror showing us the gaps in our knowledge. Maybe those gaps hide new physics, dark matter interactions we haven't modeled, dimensions we can't perceive, or forces beyond relativity. Or maybe, just maybe, the cluster is teaching us something even more profound. That discovery isn't about finding answers, but learning how to ask better questions. So here's to the unanswered, the unexplained, and the downright bizarre. Whether it's the phantom radio signals or the cosmic echo that repeats every 17 hours, these aren't just puzzles for astronomers, they're invitations. Invitations to stay curious, to wonder, and to keep looking up. Which of these 25 phenomena left you staring at the screen, mind buzzing with possibilities? Drop your favorite in the comments, hit subscribe, and let's keep unraveling the universe's greatest mysteries, one cluster at a time.